Hello, everyone. The following is the first in a series of lectures covering Chapter 41. We discussed in the last chapter that there is this uncertainty to how well we can measure a particle's position and momentum. There is a hard limit, and that's due to the fact that a particle isn't just a little point floating in space, but it also has properties of a wave. So that adds the constraint that essentially, if you can fully put your finger on where this wave particle is, then you would know nothing about its momentum. And on the other hand, if you fully knew its momentum, then the quantum particle will have to essentially be possibly able to exist anywhere in space, and then you wouldn't be able to then say it has a specific position. So when it comes to describing things like the position of a particle from the perspective of quantum mechanics, you cannot determine an exact position, but rather you can determine some general region where the particle is. So if you're wondering, can we find this particle, um, a few centimeters to the left of an atom, then the answer to that is, well, there's some uncertainty, but what we can find is the chances that the particle will be there at all. And this has to do with the wave properties of the particle that tell you about its possible locations. We already discussed in the first chapters of this course that waves, mechanical waves, like wave running up and down a string, could be described with a sinusoidal function. We call that the wave function. And this we're essentially describing the physical shape and movement of a wave, an actual physical, oscillation happening on like a string or, through the air or some other medium. We're going to introduce a similar idea to describe particles. We're going to introduce a wave function that talks about the state that the particle is in and what areas it can occupy, where you can find it. But this wave function is not a physical, like straight up physical description of the particle as a wave. It's not describing a physical wave moving up and down, um, but rather it's describing regions of where the particle can be or cannot be. And also recall that the wave particle duality implies that a particle is going to have components of both a wave and, typical classical particles. So there's a notion of a particle having a wavelength and a frequency, which are, related to particle properties, since de Broglie showed that a wavelength is associated with the particle's momentum and the frequency is associated with the electron energy. There's a drawing below here. You can pause the video to take a closer look. So, if that's true, if there's this associations where like a particle can be represented through a wave, and the wavelength and amplitude of the wave representation are related to the momentum and energy of the particle, then what about the wave's amplitude, right? That's another property of waves we talked about in the earlier chapters. What does the amplitude of the wave representation tell you? Well, recall in chapter 40 when we talked about the quantum particle model where we had this wave packet, this kind of like beat of a wave, this kind of like envelope, this chunk of a wave, kind of like in the middle. And we said that wherever there was this constructive interference happening, wherever you could see the wave, that was a localized area. But outside of the middle region, it was essentially flat due to destructive interference. And we basically said, well, the wave's not really there; it's just flat. So it looks like wherever the wave representation of a particle has a noticeable amplitude, that's a region where the particle can be. Then that means that the amplitude of a wave tells you something about the wave's position. you can only really find the particle wherever its wave representation has some non-zero amplitude. In other words, a particle can only be localized where its wave representation um, exists. So as you can kind of see here, when we learn about mechanical waves, we had some sinusoidal waves like the one we show here at the top of this GIF that has a constant amplitude throughout. So if this was representing a particle, this particle won't be localized because anywhere in space the wave occupies the same amplitude. So that means that if this is representing a particle, then the particle can be anywhere. There's no particular region in space that has any different amplitude. Now consider this wave here, which is a series of beats. Um, if you were to pause this, this is shifting over time. You can tell at any point in time, there's regions of large amplitude like this beat here, and there's the in-between regions like this one over here, where the amplitude is smaller. So that will mean that if this is representing a particle, the particle will be more likely to be found in regions here where the beats are happening than in the regions here where the amplitudes are really, really small. And we also seen this in longitudinal waves where there's areas of maximum amplitude where it gets squished together, and areas of what's like compression and refraction, basically. So this is the squishing and expanding of a longitudinal wave, which is equivalent of the peaks and troughs of a sinusoidal wave. So the description of the quantum particles amplitude of, again, the wave that represents the particle, that description is the wave function. We use the symbol psi, which kind of looks like a trident to refer to the wave function. And this is, again, a functional form, mathematical function that describes the wave representation of a particle under the quantum model. And because a particle has this wave and particle duality, then if we are describing its wave, we are also describing its own particle nature. They're interlinked. Not only that, but the wave function can also be used to describe a system of particles. So everyday objects can essentially be described with this like complex wave function of every little bit of matter that makes it. And generally, then the most general form of the wave function will be something that accounts for every little particle in the entire system. So kind of have it here where you have a little term for every particle, or one, or two, or three, and so on. And you've also included in the functions some notion of time. So we've seen this in classical physics. When we talked about the sinusoidal wave on a string, we had a wave function for that described how the little bumps in the wave were traveling through the string over time, right? So there's some notion that waves can sort of shift over time. So hence the a term for time gets included in the wave function. And the function can be simplified a little bit, kind of written in less terms, but just having a general term to refer to any particle in the system, and multiplied by this exponential function that accounts for the time component, the time dependency, how particles can kind of shift over time. So even though wave functions essentially are able to describe the wave nature of a system of particles, for the purposes of this course, we'll only discuss wave functions that only talk about a single particle, and we'll ignore the time independence. The time dependence really is just an extra factor in the formula, so we can just ignore it and just focus on the wave function, which on its own has no time dependence. It really just depends on what region the particle is occupying. So the wave function for a single particle, and assuming we're just using the time independent form, basically describes what state the particle is in. If we take the modulus of it, which is when you take the function and multiply it by its complex conjugate, you obtain the squared modulus. And this is just a way of basically obtaining a value that's always real and positive. So wave functions, because they're describing a quantum particle and they're not directly describing, physical quantities like position or velocity, the wave functions can be complex. They can have complex terms in them because, again, they're not a direct physical measurement of anything. That's why complex terms are allowed in wave functions, since they kind of give you more flexibility in further measurements. Now, that said, if we have a wave function, again, of this function that's just describing a single particle, it turns out that we take the square modulus of it. So if we just basically square the wave function, we obtain what's called the probability density. So the probability density basically tells you how likely you are to find that particle in some unit volume. In the same way that if you have mass density and you know how much volume of some material you have, then you take the mass density times the volume of material you have, and it'll tell you how heavy that material is. Or, if you know the charge density of a wire, like the linear charge density of a wire, or you know how long your wire is, then multiply that by the charge density, and it'll tell you how much charge you have in that stretch of wire. So probability density works the same way. Um, if you know the wave function of the particle, then the probability of finding that particle in some point in space, just any coordinate x, y, z, in some infinitesimal volume represented by dv, that probability is just the probability density of the wave function. Again, just basically the square of the wave function times the size of the volume. In the same way that mass density times the volume gives you mass, this probability density times the volume gives you a probability. So again, the wave function and then its square value, the probability density, isn't physically telling you where the particle is, but rather the probability of finding the particle in a specific region in space. So we're going to simplify the wave function one more time. We're going to make it so that we will only describe a particle in one-dimensional space, so just occupying one axis. For simplicity, let's say it occupies the x-axis. And thus, the probability of finding the particle in a small region at some arbitrary point x is equal to the probability density, again, psi squared, times the size of the interval. It's also shown on this graph here, where we have the probability density function here. In our case, this function would be psi squared, this one, and basically the probability of finding the particle at some point x in a region, in a tiny region around this point, is equal to the function times the size of the region. Furthermore, the probability of finding the particle in some region in the x-axis is equal to the area under the curve, under the probability density function. So if I measure the area between points A and B, this area tells me the chances of finding the particle between A and B. To calculate the area under the curve, we have to use an integral. So an integral basically is a mathematical way of saying I need to get the area under the curve. And we're not going to get too much into integrals, but I do recommend reviewing the Appendix B, Section 7 of the Zero-Way textbook for a quick guide on how to use them. So again, the fact is that because we have probability density, we need to multiply that by some space, by some length x to get probability, um, but to do that properly, it needs to be done through the idea of an integral. So there's no way about this than using integrals to get probabilities. Also, it's worth pointing out that to find the probability, you cannot get the probability of finding the particle at a single spot. You can only calculate probabilities like this, where you find the probability of finding the particle in some region. So you'll never know a particular spot's probability, but particular regions, yes. Now, the idea is that the wave function and as a probability density describe where the particle is. And the particle exists somewhere in space. So if the area under the curve gets you the probability of finding the particle in that region, then if we take the total area of the whole curve, we should get an 1. We should get the number 1. That is a probability of 100%, basically saying that the particle exists somewhere. So the probability of finding the particle anywhere in space has to be a total of 1. So the probability of finding a particle somewhere between, negative infinity, infinitely away from the x-axis, and positive infinity, infinitely on the right side of the x-axis, is equal to 1. 100% chance of finding probability between negative infinity and infinity. This condition ensures that the particle exists and is called the normalization condition. For a wave function to be legal, it has to satisfy this condition, and when it does, we say that the wave function is normalized. There's something else we can do with a wave function, which is obtain expectation values. So every time you measure the particle, its position's going to change since there's uncertainty. There's only a probability that you'll measure it in a particular place. But over a series of measurements, more often than not, you will tend to find the particle in a particular spot. So that's called the expectation value, which is where you're more likely to find the particle after enough measurements. So that's kind of saying, like, what's the average value of the particle's position if you keep measuring it a couple of times? What's the most likely value? So you can find the expectation value for, say, the particle's energy or momentum or velocity, but now we'll only discuss the expectation value of the particle's position, which can be found by, again, doing an integral. And in this case, it's kind of like what we did where we found the probability by integrating the probability density, but now we actually insert the value x in the middle of this multiplication that's happening. So we basically have the wave function here times x times its conjugate. And again, its conjugate is just a function, but any complex terms, any complex numbers in it, when you take the conjugate, get flipped. They get a negative sign added to them or a positive sign if they're already negative. But again, this is just a way of measuring what the average position, what is the most likely position of the particle on the x-axis that you'll find if you measure it a couple of times. So don't worry too much about the calculus that's going on here. It's just taking advantage of integrals and some rules about them to solve the question. But just want to explain the concept of the question, which is saying that we have this wave function here that's describing some particle, and a here is just some constant. But we're saying that we want this function to be normalized. We want it to exist somewhere in all of space. So clearly the constant here has to have some value that satisfies the normalization condition. And the condition is that, okay, the probability of finding the particle in all space has to equal 1. So from there, they do some calculus tricks to determine what A needs to be and just kind of solve for that. And then they can get the expectation value. So What they do is they just follow the formula for the expectation value, which they take the wave function here and they conjugate. The wave function has no complex terms, so the conjugate looks just like the original wave function. Nothing gets flipped because there's no complex terms. And then what follows is just integral calculus to figure out the expectation value, and they get 0. The expectation value is x equal to 0. And that makes sense because look at the amplitude of the wave function. The function here is strongly localized in the middle. So even though, there's some chance that you'll find that, over here, the most probable area where you'll find the particle is right around the middle. So more often than not, it'll be in this region. There's only like a very small chance you'll find it, say, over here. And the function then kind of flattens as it goes off. So it's very unlikely you'll find it, far away from the center. Now, there's a very, very simple wave function we can talk about, which is the free particle, and that's just a particle with no constraints. So in the real world, every particle, like electrons, protons, neutrons, whatever, are tied to some nucleus or some atomic structure. So there's some boundary to them. But just to sort of present a simple particle, let's just say there's one that's unconstrained. And basically, that means that there's no walls stopping it from going anywhere. It essentially exists as a single wavelength wave anywhere in space with no boundary conditions. And due to that relationship between a wave's wavelength and the momentum of its particle representation, if it's just one wavelength, then we know the exact momentum. Now, the wave function that describes this free particle is written right here. And essentially, A is some constant amplitude where its actual value depends on whatever the normalization condition is. So A is called the normalization constant. It just ensures normalization is accounted for. And then there's this term here, this exponential term, which can actually be written as a cos and a sine term that includes the wave number k. And this, again, is related to the wavelength of the wave, which is the same idea that we've seen in simple harmonic motion, where k was always 2 pi over lambda, the wave number. But then still remember that in this case, the wave represents a particle. So the relationship between k follows the same relationship between lambda and the particle's momentum. Note that the wave function, when we talked about simple harmonic motion, was some amplitude times a cos or a sine function, right? But in that case, we were talking about the actual position of an oscillator. This wave function doesn't describe something's actual position. It just kind of describes the state of a particle and where it's likely to be found or unlikely to be found. So it's not physically describing a physical position or a physical velocity or anything like that, which is why this wave function can have a term here that's complex, because it's not physically measuring anything. So if you consider the wave particle in this quick quiz, we're basically asking at what value of x the particle most likely to be found. So recall what I said, that a free particle exists anywhere in space by definition, and that means that it's unlocalized, so that would have then only a single wavelength. Because if you had more than one wave component in the free particle, then there would be an overlap of different waves and there'd be some localization. So to have a fully unlocalized particle, you need its wave representation to just have a single wavelength. And if it has a single wavelength, then it has a single momentum. The momentum then is precisely known. But remember Schrodinger's uncertainty principle. There is a lower limit on how well we know momentum and position. So if we know the exact momentum, then we do not know the position of the particle at all whatsoever. It could be anywhere in space for all we know. So the particle can be found anywhere along the x-axis. The amplitude everywhere in space is the same, so there's no localized region at all on the x-axis. the amplitude is independent of your position on the x-axis, so everywhere is just as likely to hold the particle. Because again, it's a free particle. If you compare that to this particle here, it's not free, right? Because it's localized in the center, and then the amplitude drops to zero. So it's more likely to be found here than anywhere else. Anyways, that's all for now. I hope to see you next time.